Welcome back everyone. In this lecture we will continue with the cardinality. So, we will focus on countable sets. Let us first see some characterization of countable sets. So, recall the definition of countable sets. So, a set X is said to be countable if either X is finite or X is countably infinite. Okay. So, now it is not difficult to actually see that the definition of countable can be reinterpreted using maps. So, now what we are going to say, like we will give equivalent characterizations, say that X is countable set, which is equivalent to saying that you have always an injective map from X to n. There exists an injective map F from X to n. So, now that even for finite sets we have injective map, again for countably infinite sets also we have injective map. So, that is what it says. So, it includes both the definitions, and similarly you can also say that there exists a surjective map from n to x. So, now the way we prove this, again the argument will be very similar to what we have done before. So, let me just prove one or two implications. So, 1 implies 2 is trivial. So, 1 implies 2 is easy, because if x is countable, then x is finite or countably infinite. If it is finite, you have bijection from x to in is embedded inside n. So, you have an injective map, and if it is countably infinite, anyway you have a bijective function from x to n. So, 1 implies 2 becomes easy. So, now why 2 implies 3? So, what we have is actually an injective map from x to n. So, what we need to do is we need to define a surjective map, again which is easy, because you start with the injective map. Let us call f is map from x to n, which is injective. So, now what we can do, we can define this map G from n to x. So, this map how it is given. So, let us see. So, f is given from x to n, which is injective. So, now you have defining a map from n to x. So, now what you do, you just take the image of x. Okay. The image of this f is going to be subset of n, and then whatever element that you are seeing there, for example, let us say some x is mapped to nx. What you can do, you can take that nx and then send it to x, okay, because x is f is injective. So, this map nx goes to x is well defined map. So, basically what we are doing, we are taking n and then sending it to its pre image under this n. Okay. Let me use this notation, because f inverse of n is an element of x. Okay, that is what we are doing. And for the rest of the elements, so this is for all n comes from the image, because there are some elements which are not in the image. What to do with them? If n does not come from actually the image, if n is not come from the image, you pick randomly one x naught, okay, fix x naught in x, okay, and then you just simply send n to x naught. If x is empty, then there is nothing to prove. So, assume that x is non empty to begin with, then you fix one x naught in x, and then you send all the elements which are not in the image to that particular x naught, and whatever is in the image you can send it to the pre-image, no issue. So, this map is easy to verify that G is surjective. Okay. So, now to see actually why we get 3 implies 2, which is again easy. So, 3 implies 2. Suppose if you have a map, let us say G from n to x. So, now what you can do, you can define this f from x to n. So, let us say this is given surjective map. Now, define this f such that look at the image. So, take an element x in x, look at g of x, sorry, g inverse of x. So, this is going to be a subset inside n, then pick minimum and then you send it to that. Okay. So, map x in x to the minimum of g inverse x, and using the similar argument that I gave earlier, you can prove that this is indeed injective map. So, that tells that given surjective map you are able to always get an injective map from x to n, and now it is an easy exercise to prove that 2 implies 1. I will leave it to you. So, prove 2 implies 1. Okay. So, this gives indeed characterization of countable sets, and whenever you have an injective map from x to n, you know that it is injective, it is countable, and whenever you have surjective map from n to x, again you have countability. Okay. So, now let us actually focus on this various countable infinite sets. So, we have this counter diagonalization technique that actually tells you that interestingly many operations like countable union of countable sets and like Cartesian product of countable sets, all of them will be countable. So, to prove all these statements one needs to actually understand why n cross n is countable. So, all we need is that. Okay. So, first we are going to say that n cross n is indeed countably infinite, and using this and arguments in this you can actually say that any like the similar, using similar argument one can say that Cartesian product of 2 countably infinite set will be countably infinite. Similarly, Cartesian product of 2 countable sets will be countable sets. So, let us actually look at what goes into the proof. So, you are interested in actually finding a surjective map from n to n cross n. So, that is what we are interested in doing, or you have to get an actually injective map from n cross n to n. Okay. If we are able to do one of them, then we are done. So, let us try to do actually both. Okay. So, and then you will see that the proof, each proof actually relies on some interesting combinatorics and algebra. So, let us first construct this surjective map, which is actually generalizes to other sets as well. So, let us write this n cross n as follows. So, we just simply write it as 1 1. Okay. So, our n is starting with 0, let us start with that. So, you have 0 0, 0 1, 0 2, etc. And similarly, here you have 1 0, 1 1, 1 2, etc. So, basically I am writing it as this infinite by infinite matrix starting with 0 0 and so on. So, now you can see the pattern. So, how it actually written. now what we want to do is we want to actually give a surjective map from n to n cross n. So, find a surjective map from n to n cross n. And if you think about it, the surjective map corresponds to basically counting n cross n from 0 to infinity. So, basically you are listing all the elements of n cross n, that is all. Okay. That is what the surjective map means. Okay. You keep counting. So, sometimes same element may be counted twice, but in this case it is not happening. But anyway, so this is what surjective map means. So, now what you can do, like of course, the problem is that if we start with counting from left to right, then we do not know where to actually end, because you start with 0 0, 0 1, 0 2 and so on, it never ends. Similarly, if we go like start with top to bottom, again we do not know where to end. So, this is actually leads to problem. So, Cantor actually came up with this very nice trick called Cantor diagonalization, which actually instead of going from left to right and right to left, you go zigzag. So, you just take this diagonal path, you start with here and then move to 0 1 and then come back to this 1 0, then go to 2 0 and then go to 1 1, then go to 0 2 and then go to, so here you have 0 3. So, you go to 0 to 0 3 and then you go like this and so on. Okay. So, now it is clear what is the pattern. So, basically you have these numbers are written. So, you are actually taking the path like this. So, diagonally you are actually counting, and then you can see that by doing this diagonal thing, you will be able to actually count all of them. So, that means, so I am just telling that this is my first element and this is my second element and this is my third element, this is my fourth element and this is my fifth element, this is my sixth element and so on. So, basically I am actually telling exactly, so maybe because we are starting with 0. So, maybe I should say that this is my 0th element and this is my first element, this is my second element, this is my third element, this is my fourth element, this is my fifth element and so on. Okay. So, this defines indeed a map from n to n cross n, and then you can see that this map is indeed a surjective map, and one can actually come up with very explicit algebraic formula for this map, and I will leave it to you to actually check what is that map. But this map is, you can see that it is abstractly defined map, it does not require any algebraic formula, but in this case one will be able to give algebraic formula, but let us not worry about it. And this proves that n cross n is indeed actually countably infinite, because it is infinite and it is countable. So, it is countably infinite. So, now you can use the same technique to prove A cross B is again countable or countably infinite. Okay. So, if is countable if A and B are countable. Okay. So, how do we do this? You can see that if A and B are finite, then there is nothing to prove, because both are finite and the cardinality of A cross B will be cardinality of A times cardinality of B. So, that is something one can check directly. So, maybe that you can take it as exercise. Suppose cardinality of A is n and cardinality of B is m, then you can prove that cardinality of A cross B is n. Okay. So, now what we want to do? We want to actually prove that A cross B itself is countable when A and B are countable. So, if one of them is infinite, then it becomes countably infinite. Okay. So, you can deal with each cases similarly. The most non-trivial case will be if both of them are countably infinite. Again you can take if one of them is finite, it is not very difficult to prove. So, for example, if A is finite, you can write it as like A1 etc. AN. So, then it is clear that how to write the A cross B elements, because B is countable. So, you can write it as B as B1, B2 etc. So, now if you assume B is countably infinite, there are infinitely many elements. So, now what you can do, you can actually write this as A1 B1 and then again A1 B2 and so on, the way we wrote it before, and similarly you have A2 B1 and then A2 B2 and so on. Similarly, A3 B1 and A3 B2 etc. So, now all the elements of A cross B can be listed like this. So, now what you do, you just use this Cantor diagonalization. You start with this, then you go to this and then go to this and then come to this and then go like this. So, and so on, you will be able to count all of them. So, then you will be having a natural surjective map from N to this A cross B. So, that proves that A cross B is again countable. And this technique can be actually used in order to prove, for example, countable union of countable set is also countable. Okay. So, maybe like the best way to do is you can write this countable union of countable sets as image of like n cross n. Okay. So, that is easier. So, because let us say I have countable sets, okay, AI's are countable and I is also countable. So, now what do we want to prove? The claim is that union of AI INI is indeed countable. Okay. So, if you think about it, since AI is countable, we will be able to list it as AI1, AI2 etc. Okay. So, I am listing it from 1 to etc. because nobody counts like 0, 1, 2. So, it is okay to actually just start with 1. Okay. For that purpose, let me just introduce this z positive, which is the set of non-negative integers, sorry, positive integers. So, which we call list it as 1, 2 etc. Okay. Usually when you are counting, you always use 1, 2, 3, not 0, 1, 2, 3. So, it is okay to write 1, 2, 3. So, now each I you will be able to list it as AI1 etc. AI2 because you have a surjective map from N to AI. So, because we have a surjective map from N to AI, so given I is mapped to, let us say, sorry, given J, let us say it is mapped to AJ. Okay, that is how we are actually defining this images. So, we have listed them. So, now when you are taking this union, so what happens? So, you can see that the union is again written as, okay, you can just list them as follows. So, of course, some of them could be listed multiple times, but we do not care. So, if I is indeed countable, so then the I is also written as some I1, I2 etc. So, then you will be having something like AI11, AI12, AI13, sorry, the other way, yeah, it is correct, AI11, AI12 etc. So, I am listing all the elements like this and then AI21, AI22, AI23 3 and so on. So, the same diagonalization techniques that I am using, but I am doing it in the sets. So, A I 3 1, A I 3 2, etc. This is how I list. So, some of the elements could be repeated, but I do not care. So, now you can see that the same diagonalization technique that we used can be used to count this. You can go via the diagonal and then you can actually go like this. Okay. So, that actually tells you that which element should be the first element, which element should be second, third, and then fourth, fifth, sixth, seventh, eighth, and so on. So, it defines a map from n to the union of ai, I n I, and it is a surjective map that tells you that the countable union of countable set must be countable. So, now we already proved that the Cartesian product of two countable set must be countable, and it is not difficult to prove that if we take finitely many Cartesian product of countable sets, that is again countable. Okay. Cartesian products of finitely many countable sets is again countable. Okay. So, it is a very important observation, and now using whatever results that we have proved, we can actually prove that for example, the set of natural numbers is indeed countable, and similarly integers is countable, and this would imply that q cross q any number of times is countable, and similarly z cross etc. z any number of times is countable. Okay. And the most interesting case will be the polynomials over z and the polynomials over q, both of them are countable. Okay. So, this is not very hard to prove. So, maybe you can take it as exercise. So, one way to do is like you can think q as union of q r, where r comes from z positive, where q r is defined to be those rational numbers whose denominator has r in it. Okay. So, where p or are relatively prime and p comes from integers. And now it is not very hard to see that each individual q r is countable. So, q r is countable, and now that would imply for all r that q is countable. Okay. So, this is like one way to prove that q is countable. Again, there is a easy way to actually define a surjective function from z cross n to q. Since z is countable, n is countable, z cross n is countable. So, you have a surjective map from n to z cross n. Okay. Now, if you have a surjective map here, so then that also tells you that q is countable. So, what is this map? This map is just take some m and n, send it to m comma n, sorry m divided by n. So, here we will take the positive integers. Okay. And by the description of rational numbers, which we will construct later rigorously. So, any rational number, you know that it is just a ratio of some integer and positive integer. So, using that you can see that this map is surjective, and this would also tell you that Q is countable. Indeed, it is countably infinite. Okay. So, now the way you go about this Qx or Hx. So, you can actually write Qx as union of, indeed disjoint union of, again Q R x, where R will come from non-negative integers, where Q R x by definition, the Q R x you take it to be degree or polynomials. So, maybe let me do it rigorously, maybe it is required later. So, you take Q x, write it as disjoint union of R from zero to infinity and degree or polynomials. Okay. So, now what will be the degree or polynomial? So, the degree or polynomial Q R x is given by A r x power r plus etcetera plus A 1 x plus A naught, where A r should be supposed to be non-zero. So, now it is not difficult to see that this Q r bracket x has natural bijective correspondence with Q non-zero, because that is where this A r comes from, cross all other elements you can freely take it from Q. Okay. So, this is the constant term A naught, this is A r minus 1, this is A r. Actually, if we think about it, one can also divide by A r, but anyway we do not need to worry about it. So, there is a, like, at least one can easily see that there is a natural surjective map from this Q cross Q cross Q times Q difference 0. So, this is exactly the R copies. From this to Q R x we have a map. What is the map? The map is given by, take this tuple A naught, sorry, A r minus 1 etcetera A naught, and then send it to this polynomial A r x power r plus etcetera plus A 1 x plus A naught. And since this map is surjective, so that would imply that this is countable, because countable product of, sorry, finite product of countable set is countable. So, this is countable, and that would imply that this is countable, and that would imply that this union is countable and this is countable. Okay. So, that is where you can prove Q x is countable. Similarly, one can prove that Hx is countable, and so we just define uncountable sets to be sets which are not countable. So, for example, one can prove that real numbers or any interval like closed interval, open interval and so on, they are all indeed uncountable. Okay. So, maybe like those facts you will be seeing it in your analysis course. So, I am not going to get into much, maybe I am going to just write it as exercise that R closed 0 comma 1 or closed A comma B or open A comma B. So, all of them are indeed uncountable. So, you can actually read more about uncountability in your analysis course. So, what we will do in the next class, we will actually prove that this Schroeder's-Bernstein's theorem, which talks about when two sets can have same cardinality. So, one can expect that for example, if you have an injective map from A to B, injective map from A to B and then another injective map from B to A. So, in this situation one want to say that the cardinality of A must be equal to cardinality of B. That means, we should have a bijective map from A to B. Okay. So, that is indeed guaranteed by this Schroeder's-Bernstein's theorem, which is very interesting theorem. And indeed what we want to say that whenever we have this injective map, we want to say that the cardinality of A is less than or equal to cardinality of B. Since we do not know how to compare the cardinalities, it is too dangerous right now to say this, but once we prove this Schroeder's-Bernstein's theorem, then maybe we will be able to define that cardinality A is less than or equal to cardinality of B if there is an injective map from A to B. Okay, I will actually stop here. We will continue with the Schroeder's-Bernstein's theorem and little bit of discussion about other types of infinities in the next class. I will stop here. Thanks.